This session is actually sponsored by Mosaic, and so we want to thank Adam Herges, who's standing there in the back of the room. If you ever need money, go to Adam. And yeah, we really appreciate the support for this. This session I'm very excited about. So I sat in Andrew Margonaut's office about a year ago, and we were at University of Illinois, and we are talking about, what could we, and Adam actually introduced me to Andrew as well. And we were talking about what can we do for a legacy phosphorus session, and we put together a list of names of people that we'd like to participate, and luckily we got all of them, I think. And Andrew just said, there's only one thing. I've been traveling a lot, and I have to make sure that my wife lets me go to this. And luckily, you got the hall pass. So it's great to have Andrew here, one of my favorite phosphorus researchers in the world. So I'm very happy to have him leading this session. And I think we have a great group of people, and we'll be introducing them as the day goes on. But I should probably start with an introduction of Andrew. So Dr. Andrew Margonaut is a soil scientist and associate professor at the University of Illinois at Urbana-Champaign, which is my alma mater. And also Anna Maria Marshall and some other folks here probably are from UIUC too. He leads a research team of about 40 people, 58. I think that's gone up by about 18 since I saw you. Okay. He leads a research team focused on soil fertility and nutrient management in agroecosystems, particularly in the U.S. Corn Belt. His work spans phosphorus research across scales from molecular to watershed levels and from a single growing season to the past century. And he really has some amazing data from the state of Illinois across the state. His team takes a biogeochemical approach to studying soil functions with an emphasis on soil organic matter cycling, nutrient use efficiency, and off-farm losses. So Andrew, I'm going to turn it over to you, and we're not going to have the comments we talked about earlier, so we'll just go straight into it, and we'll let you take off. And for some reason, there we go.
Alrighty, well, is this going through? Perfect. I'm Andrew Margonaut. Thank you, Matt, for the introduction. I'm a soil scientist, and I've been working on phosphorus for probably 14 years now. Got my start in weathered soils in the tropics, and from there fell in love with initially the not enough of the Goldilocks that is phosphorus, right? Phosphorus is the Goldilocks element, at least that's how I think of it. There's oftentimes too little or too much. Getting it just right is a persistent challenge. So I got my start with the inverse of legacy P, of not enough. We're talking systems in East Africa and South America. And now this special session is focused on the situation of the opposite, which is a little bit too much. So the talks that we have today, I'll kick it off, focus on the opposite situation of there's a little bit too much or there's way too much phosphorus. The term of art currently seems to be legacy phosphorus. And what I want to do in my opening talk for this session is lay out some definitions and some considerations of how the definitional aspect of legacy P is not trivial. There's not consensus, and why that may or may not matter. So after myself, we have a series of other speakers. They're each giving 25 minutes, and they will get at legacy P in different angles, from things like uncertainty to modeling, et cetera. So I think it's a very nice lineup that we have today. Alrighty, so with that, I'll kick us off. I want us to begin in this session by laying out some definitions. I'd like to offer up some thoughts on the quantification of legacy phosphorus. It's typically thought of as a positive mass balance. There's more P that went in, that came out of the system. However you define the system, that's a different question. And I want to try to diagnose what I think are persistent challenges to moving forward. And if we can't solve these gaps in the quantification, we might just spin our wheels for the next 20, 30 years. So that's the goal, and then I'll offer some potential ways forward. So first, this is all funded by different groups. They're shown there, thanks to them. I'll begin with the overview of the terminology of legacy phosphorus. In short, it's a very new term. We've usurped the historical term of residual P. There's implications for how we think about it. Then we'll talk about how we can quantify legacy phosphorus. And quantify might be a strong word. I would say we're probably estimating legacy phosphorus on a good day. We'll talk about specifically, I'll pick on my favorite technique for its estimation of balances, a classic tool in biogeochemistry, in agronomy, and there's some issues with the long time scales that are presented by legacy P when it comes to useful mass balance estimates. And then we'll talk about some proposed approaches. And these are not low-hanging fruit. That's all been picked. It's the high-hanging fruit. It's going to be difficult, but then I think that we can all agree this is an important challenge, but it's going to have some challenges then in the approach to quantification. Alrighty, so with that, I'd like to begin with these definitional offerings that we've seen. If you've not been aware, there's been a series of papers, a flush of papers published in the last 18 months, specifically on how do we define legacy phosphorus. There's a couple more coming out the publication pipeline from what I've seen at different journals. So clearly, researchers don't quite agree on how we should be defining legacy phosphorus. And not even in soils, just as a general term. Watersheds are a scale of relevance here. So this is a final paper that I'll dive into a bit more from my colleague and I, where we tried to, in a moment of confusion on a Friday afternoon, we sat down and had the discussion of what the heck is legacy P? It's used as a synonym with other terms. Can we make some clear understanding of why different terms are used in different ways? And so what we found was if you try to track the two major terms used to describe this accumulated phosphorus, two terms pop out. One is residual, the other is legacy phosphorus. And shown here is a plot since 1920 through present day, the number of publications that use these two different terms. And to give you some background here, residual phosphorus was first used for the concept that we now describe as legacy P. And that concept is phosphorus from the past that is built up in the system. And the context here was 1925, Iowa, and it was an agronomic term used to describe the intentional buildup of phosphorus. Do you add 10 years worth of P up front, or do you apply P every year? And that was the specific study in question here. So that's 1925. That's 100 years ago exactly. We don't see the word legacy P until 1996, at least from what we scoured in peer-reviewed publications. And the context for legacy phosphorus that emerged 30 years or 29 years ago is wetlands, and specifically where Django works in Florida, in the Everglade context. And here there was no inference to the source. It wasn't about fertilizer or sediment. It was simply P that's in circulation in the riverine system of the Everglades. That's all it was meant to be. So as we can see, there's more publications for residual P, but the trajectory is similar between these two terms. So this, I think, is important because there are connotations from the historical origins on the two terms, and they're a little bit different. So if we take the younger term, younger by 60 plus years, legacy phosphorus is a broader scale in terms of the watershed. This is how it was intentionally used in Florida in 96. And residual is more of the pet-on scale, or let's say even the field scale, and it has more agronomic implications. So one is about fertilization, which is residual P. One is about, well, it's agnostic to the source of phosphorus or the time scale in which it was entrained in the system. So I'm not here to fight about definitions. I have no dog in the fight. It's more just to point out that we should be cautious because different camps might have different connotations in their head when we drop a certain phrase for this built up phosphorus from the past. We can go further. In this recent piece that we just published, we did a non-quantitative compilation of existing terms, and two observations that we make here is that these are all trying to get at the same idea that we're in this room here to discuss, this accumulation of past P. They're oftentimes in binaries, yes, no, black, white. In these cases, things like old versus new P, source-wise, anthropogenic versus geogenic. And I think whenever we've got binaries, we have the issue of incommensurability. We've got incommensurable definitions. We're talking past each other. So these different binaries simply emphasize different dimensions, different perspectives. So for example, the very first one is about age. Then the second one there is about source. Those aren't wrong or right. They're just different takes, different angles or dimensions on the same concept. So we might need to be more open and think about a multidimensional approach to defining this kind of phosphorus. So that's a few thoughts on the definitions. Definitions matter insofar as knowledge transfer. That's why we do taxonomy of soils or of species. We're all on the same page. So there's, I think, a lot of room for some kind of consensus building to be done on this. Apart from that, if we define for the purpose of this session, legacy P, as Matt said, as this intuitive concept like soul health, it's fuzzy, but we all agree more or less that it's accumulated P. I want to now talk about how we estimate or how we quantify it. So there's four major approaches to coming up with a number of how much P has been built up in a system, whether you define the system as one season for one field or an entire continent over 30 years. We're not talking about those boundaries just yet. So one is mass balances. You know what's going in, you know what's going out. A positive mass balance would be legacy P. A second is long-term studies, experiments where we can track the inputs and outputs. And these can bleed over categories. We can do a mass balance in a long-term study, like say the Rothamsted experiment from 1843 in the UK. Third is soil test P trends. This is the quick and dirty shooting from the hip. Farmers do this. It is not quantitative, but it gives you a qualitative, meaning is it going up or down, build up. And fourth would be a chronosequence, a technique in ecosystem biogeochem, where you do space for time substitution. You don't have to wait 30 years for the study to go. You find sites of varying age in one moment in time. And these approaches are individually inadequate. Not one approach here gives us the kind of confidence by itself that we would need to talk about how much legacy P. But they're also complementary. We can combine, we can fuse these to decrease uncertainty and increase confidence. And third, and this might be a big kicker, is that some of these approaches are only feasible for various reasons and may only make sense at certain scales of space and time. Hence this figure. So I think of this figure as the Here Be Dragons maps of the 1200s, where there's a lot of gray zones, blind spots, where we don't really know what's going on. The green space is where we propose a lot of research is ongoing. And this is sort of the street lamp problem, right? You only look for your fallen wallet beneath the street lamp because that's where the light shines. But if you drop the wallet elsewhere on the street, you're not going to find it. So a lot of the research happens there because it's the low-hanging fruit that I was getting at. So we should think about some things like, are there certain regions where it does not make sense or it's not feasible to quantify legacy P? Those are these regions in red. And are there regions where it does make sense and it's going to be hard, but it's at least technically feasible? And that would be these blind spots in the gray zone. And I want to walk through two examples of different space and time scales using examples from, as Matt said, Illinois. So for this, we will go back to 1870s. We'll go back 150 years and look at some evidence on legacy P in terms of how much and how to quantify it. And I'm going to pick on mass balances. I think this is because mass balances are the most useful tool. It's easy to do, and it's easy to get a wrong number. And I'll show you some data on why we should be a little bit more careful and where there are places to be better on getting better numbers. So a bit on mass balances. A mass balance is simple. It is like your bank account. Money comes in, money goes out, and the remainder is the balance. So legacy P, by definition, in this concept, is a positive mass balance. There's more P going in than coming out of the system. Now, typically, when it comes to cropping systems, the major P influxes are going to be fertilizer or manure. The outfluxes are going to be biomass harvests, typically grain, but also meat, bone of livestock. Losses are generally a small part of the export balance. So here's an example. This is going to go for large space and large time scale. This is going back to 1945, so only 80 years. And this is for the space scale of Illinois, so specifically 21 million acres of cropland. This is a figure readapted from Mark David's work, and it was a mass balance of P through 2000. We've extended this mass balance through present day. And what I want to point out here is that we had a large period of a positive mass balance for about 30 years or 25 years, from 1960 through 1990. And note that we were in a negative balance before this, before we had fertilizers, as Brian had talked about yesterday. And since 90, we've been under fertilizing crops. So less P is going onto croplands and is coming off with bushels of corn and soybean. Now, the key thing is that a lot happened in a short time scale. In those 80 years, we had a large, meaning of 4.9 billion pounds of P, not P2O5, but elemental P buildup. That happened in roughly 1/3 of all the time shown on this figure. That seems like a lot, but to give some context, if we understand how much P is naturally in soils in Illinois, it's only about a 5% enrichment because we estimate 95 billion pounds of P to 3-foot depth across our croplands. So this is important though, because if that 5% enrichment is in a form and in a location like the soil surface that's liable to loss, then we have problems. We then continued this mass balance through present day, 2017 through 2022. Spatial scales here now are going down. We're looking at county. The number at the very top is the state average. So there can be, as we all know, at sub or lower spatial scales, more variability in balances. So the state is negative, but there are counties that are positive as a result. Why do I bring this up? Well, in the same 5-year time period as these balances that we see, 2017 through 2022, Illinois experienced a large increase in state P exports, a 35% increase. And that was in spite of the point sources meeting their reductions. So the non-point source sector, which includes the ag, but it's not just ag, effectively canceled out and then increased P losses. But we weren't over fertilizing with phosphorus. So an apparent paradox, right? We see record losses of phosphorus, and yet we're under fertilizing. We're in a negative P balance. And this gets into a theme that balances are not always a great tool for predicting loss risk at certain space-time scales. This is an example of why balances are useful, but we have to be careful because in this case, a negative balance is not explaining increased losses. Okay, so then to put this concept, this is the first of 2 problems that I'm going to diagnose with mass balances for phosphorus, is that theoretically, we would expect this. At neutral balance, there's no losses on the y-axis. And as we increase the positive balance, we would hypothesize that there's more losses. Especially for nitrogen, this is often postulated. Now, whether it gets exponential once we hit a threshold of an increasingly positive balance, like we see for N2O and nitrate, that's kind of up for questions for phosphorus. In reality, what do we see? Well, it gets messy like this. This is conceptual, but there's papers that support this. We also see losses, as you just saw for the state of Illinois, where we are in a negative balance, and we still see losses. And so if you look at different scales from state to county to field, oftentimes there's not a great or no correspondence between the P balance, including a positive, i.e. legacy balance, with contemporary losses. Now, why might this be? It might be issues of time scales. The losses being predicted by the balance, that relationship may not manifest at short space timescales for reasons like immobilization of excess P in soil, for reasons of fixation, for reasons of lag effects. P is sluggish, nitrogen is fleeting, so they behave differently. So that's high level space. Let's go larger scale in time from 80 years to 150 years and smaller scale to the plot field scale. And for this, we're on the map there of the Here Be Dragons on the border of whether it even makes sense to go deeper. And we're looking at the Morrow plots. This is the world's second oldest continuous study located at the U of I campus. And I want to share some results from this because it's a unique resource to tackle these questions. We have kept records on inputs and outputs via fertilizer and yield since 1888. The experiment began in 1876, and this might just be the best quality data set to help diagnose the issues of mass balances to predict legacy P in soils. So this study began in 76 as a crop rotation study on corn production. We added in 1904 fertility treatments, including rock phosphate, bone meal, and we can trace the trajectory of different P fertilizer types throughout the ages, as Brian talked about yesterday. But the point stands, we have really good records exceeding 135 years on inputs and outputs. So what did we find from the Mara plots? Well, what you're seeing here is 3 of our 24 treatments. And I've picked out a few of them in green with the large positive P balance. Red is a more minor one. And then the unfertilized but still cropped system, these are all corn on corn, is the gray one. So as you might expect, on that last one, if you do corn on corn since 1876 with nothing ever added, you're mining your sole phosphorus. So we see a well-constrained, there's less uncertainty and negative balance. As you get a larger magnitude of balance, the uncertainty also amplifies. And we see that for the positive balances, that whether it's a low to relatively higher positive P balance, there's more uncertainty in the total amount. And this comes from things like we have to assume a P content of the inputs. They used rock phosphate from around the 1910 period. We don't have the exact sample of rock phosphate, which is the Tennessee Brown deposits now mined out. We think we have an estimate. Think about the effluxes, like grain P content. Hybrids have changed. And so we have a decent sense from the notebooks that they had in 1905 of the P content, but we have to make assumptions in these balances. And therein lies the risk, is that we amplify uncertainty, especially over time. Like the Illinois mass balance, large spatial scale, even at this small scale of space, we find that a lot happens very quickly. So note that over half of the positive P balance we see today, so half of the legacy P today was built up in about 15 years. So 10% of the time engendered half of the legacy phosphorus from that period of high application of phosphate rock. So there's a bit of hysteresis here, right? Going one way is not the same as you go back. It's easy to build up, it's hard to draw back down. At the rate of drawdown that you're seeing there, it'll take us another century and a half to get down to a agronomically acceptable level. So here's then a second gap. The reason why I'm showing you the Mara plots is also because it's a good way to validate balances. We don't really validate a balance. A balance is on paper or on your computer. To validate a balance means you have to go from a T0 to a TX and measure the delta in soil P stock. And we can do that with the Mara plots. So you just saw the balances on paper, calculations. When we actually go and we measure the soils, we have the original samples from the 1800s. We measured them in 2021, and the stocks that we measured did not correspond to the balances that we calculated. So this is a graph showing you over time, x-axis, with the y-axis of the discrepancy. So some treatments, we find that there's more P in the soil built up than what we think there should be based on the calculation of mass balance. And in some treatments, we see there's way less than what we should be finding. And note that this amplifies error-wise over time. This is really confusing. We're missing almost 2,000 pounds of P per acre that the math says that we should have in the soil. These are not sandy soils. They're not highly eroding. We know that the P is not translocating beneath the top 12 inches. So where are the extra 2,000 pounds of P per acre? The missing phosphorus. And this is not new. There's shorter term studies like the LTAR system run by USDA published a very nice paper pointing out that uncertainty basically undermines balances. And if, as they point out, you don't have exact measurements, not assumed, but exact measurements on major influx and effluxes of your balance, like manure and grain P content, then the assumptions render, in their case, I think it was up to a third of all of their balances useless, because the uncertainty is larger in magnitude than the actual balance value. So there's a real issue here, but I think we need to get higher quality data for these balances. Alrighty, since time is getting close, I want to point out one example of why this is useful. This might concern us as biogeochemists, as crop scientists, agronomists, but modelers look to us for high quality data. So here's a nice example of it's the same exact period in time. These are balances, albeit at different scales. We've got Huck-8s on the top by Robert Sabo, and on the bottom by Bruno Ringeval from France. And he's using gridded 250-meter scale, but they're both trying to model from the period of 2002 through 2012, so the same decade, the same data they have access to. They're trying to estimate legacy P. And specifically in these examples, they're taking two approaches. Sabo on top is using a mass balance, as we've been discussing. On the bottom, Bruno is trying to use modeling. So it's a process-based model. And they find completely opposite magnitudes of balances in the same region in the same 10 years. So Sabo is finding positive balances, which I would expect for the dairy-rich part of Wisconsin, as you can see. And then Ringeval out of France is finding a negative balance. So this is uncomfortable. And they're both colleagues in France. I'm not going to pick on them here, but it just shows you two very intelligent, very expert scientists with access to the same data that you and I have are getting opposite magnitudes of legacy phosphorus. So from the balances that we're measuring with high confidence, not agreeing with what we're measuring in soils, to the modeling giving us opposite, similar magnitudes, opposite directionalities, there might be a problem here. Now, it could make sense. There's different assumptions, there's different approaches. Balances have assumptions, so do models. But this might be a thing to really sink our teeth into, because until we can get some convergence on magnitudes, I'm not sure we have confidence, and then policymakers may also lack that confidence in the how much of this built up phosphorus. You might be thinking, well, maybe it's soil test P that's of use to us. Short answer is no, it's not. If you look at soil test P, in this case, melic P, it gives you a rough directionality. So we see the positive P balance system in green, there's higher soil test P, but the system that's being mined, it's a negative P balance, soil test P does not change. So we know this. The point is that we can't use soil testing by Melick or Olson to quantify legacy P. So here's how we could maybe do that. This is an example from Illinois, but I know other states and other nations, especially Germany, are doing this now. I think there might be a need for long-term soil observation networks where we resample the same locations across a region to monitor P. The drawback is that we have to wait 10, 20, 30 years. It's not a chronosequence approach, but it's the next best thing. These are examples of the resources that we have access to in Illinois. We have an archive of samples of pedons across the states. The middle map shows you where we have 460 pedons, so full depth of soil from as far back as 1861 through present day that we're resampling. And then we have notebooks from Hopkins from 1899 through present day that let us also resample the same spot and remeasure soil P stocks as they did back then. This is useful because in this example, we can look at the net change in P stocks. These are examples from our 460 sites, 5 of them, where we can quantify what's actually built up in the soil, not what the balance we think is by calculation. And we can then link that to watershed scale, in this case, Huck-8 P export, to try to understand if this legacy soil P might explain the losses that we see today because of the lag time. So some future directions, I think building these soil monitoring networks is going to be important. I think that's a good call to action for different sectors to come together. A second direction would be the form of phosphorus. We'll hear some talks after this one about making use of legacy P. That's a question of speciation, not a question of how much. And we are very much flying blind on speciation. We know from the Morrow plots that in those positive P balance systems that built up 5,000 pounds of P per acre, it was added as inorganic P. And if you look at the right-hand side of those black lines, that's the legacy P. It is in forms that are all over the map. It's present as iron-bound P, organic phosphorus, calcium phosphorus, though it was added as inorganic soluble P. So the question then would be is, what's the form of this built-up P? And the kinetics, how quickly after building it up is it retransformed? If you don't use it within the next season, is it now diversified or is it sitting there as soluble P forms? There's implications here for drawdown, but also for losses, speciation. Okay, so with that, I will summarize this. There's different definitions of legacy P, not a bad thing, but consensus may be warranted. It might be objective based definitions. And I would say the binaries are simply a symptom of many ways to think about it. The approaches to quantify are individually inadequate, but if we couple these together, chronosequence, resampling, etc., a lot of power there. Mass balances are the most accessible approach. You just need to make some assumptions and do some math, and you can get a decent estimate. But I think I just showed you some examples from the Mara plots that we should be careful. When you validate a balance, we're finding very poor correspondence, either too much or too little, and that bleeds over into modeling. And so the modelers need us, the empiricists, to do a better job with the quantification. I think ways to address these are to begin now. It would have been nice 30 years ago, but now it's now. To begin with these long-term monitoring networks of soils, including building archives. And that will, I think, help with the ground truthing of these models that are going to be essential to scale up. We can't Swiss cheese a region with soil samples and wait 50 years for solving the how much. And apart from that, I think we have to go from the how much question, the magnitude, to the questions of kinetics, how fast, and how usable and how losable, which is a question of speciation. Alrighty, thanks.
I should said this at the outset. We've got time for a question or two before the next speaker. We are going to have a panel at the end of this where we're going to bring the speakers back up, and you'll be able to ask questions then too. And we also have some moderated questions that Andrew will be asking. But does anyone have a question or two for Andrew right now?
Hey Andrew, how's it going?
Good, thanks. How are you?
Good. So one balance that you didn't mention was one that takes into account soil P, and I think that would be most useful for policymakers, having spent some time in that realm previously. So when you and second comment on that, the disconnect between measured stocks and balance, I would argue is probably most likely the error is in the measured stocks, and that our confirmation bias as scientists, we want to believe we're really good at testing phosphorus and understanding the density of soil, and that the model balance is probably more likely to be true, and that the measured balance is probably prone to error. But I wonder if you could comment on including, soil phosphorus. So for those a balance of inputs and outputs relative to recommendation for crop response would be more useful in a policy realm, right? Like, so if soil test is above 50, then it's surplus, right? Because your crop is getting all its phosphorus out of pre-existing legacy P.
Yeah. Thanks, Josh. Just one comment on those stocks. I would bet my house that those stock numbers are accurate, only because we did triplicate cores, bulk density, we did total P by fusion. I think in the example that I showed of the Mara plots, the error I would say is from the balance assumptions. But I think you're raising a good point. Where might the measured balance be less accurate than the calculated balance and vice versa? Because I think there are situations where we probably have more confidence in the calculated balance, not the measured difference. Your question was about the practical aspects of
Policy and
Policy.
including the soil stock in your balance
sure.
for policy.
A few thoughts here. So one would be is that the balance is important to think about what the T0 is, right? So if you're starting in 2002, like those examples of the models, well, you might be missing in Illinois that there was a massive positive balance beginning in the 1960s. But if you begin it after that happened, you might miss all of the background. And so you're now counting what would have been historical balance as your baseline. So I think how far back in time to go is really important for policy, because if you miss any historical buildup, then it might lead you astray with current losses from a policy loss perspective. Does that make sense?
Yeah, I mean, we could discuss more. I would tend to disagree, but
Okay, good. That would be a good debate to have. In terms of things like offtakes and STP, I'm not at all dismissing that there is massive value agronomically and practically for producers, agronomists, and policymakers that look, a balance should be a good thing to get neutral. And if you've got a high soil test buildup, if you're at 100 pounds of millip per acre, yes, you want to draw down. There's no sense in throwing more money at that field, etc. I'm approaching this more from to have high confidence quantification. These tools fall short. Are they valuable for policy and for management? Absolutely. And so I think that we still want to estimate balances as farmers do for their maintenance applications anyhow. For policy, a balance might be a good tool, I think, to guide, but I would get concerned if a balance is being used by policymakers to predict losses when it comes to P, because I'm not convinced from what I've seen field to state scale that a P balance will give you a high confidence estimate of what you're losing in the coming years.
Let's leave it at that for now.
Okay.
Yeah.
Cliffhanger.
Yeah.
Thank you, Josh. Okay. Well, with that, the next speaker is Kim Van Meter. Dr. Van Meter is a professor who works on the watershed aspects of phosphorus. So we're very glad to have her here to give a different spatial scale perspective on legacy phosphorus. So with that, there you are, Kim. I've not met you. Sorry. Please welcome Kim. I apologize. Kim's bio is here, so if I may say a few more words about you. Dr. Van Meter is a water system scientist studying how human activities impact water quality across various landscapes. Her research focuses on legacy nutrient buildup, like phosphorus, in ag landscapes and the long-term trajectories needed to improve water quality. She is currently investigating, among many other things, the effects of climate change on the Great Lakes in North America, especially how changing water levels might be impacting coastal wetlands. Her work includes a recent NASA-funded project on wetland restoration to reduce downstream nitrate and our favorite element, phosphorus loads. So with that, please welcome Dr. Van Meter again.
Thanks a lot, Andrew. It is great to have my talk come right after yours because I think it's not only a nice background, but I think it also puts some, I guess, challenges in place for me to kind of be in conversation with as we have our discussion. So as you mentioned, I'm professor at Penn State. I'm in the geography department. I broadly work on water system science, but specifically interested in nutrient pollution, phosphorus and nitrogen in water bodies. And I'll talk a little bit about my background. I'm from Iowa originally. I started grad school at the University of Iowa and working on water quality modeling, and I was really thinking about nitrogen. You know, in the Mississippi River Basin, it's hard to talk about anything else other than nitrogen. But then I moved up to the University of Waterloo in Canada. Waterloo's part of the Grand River watershed, which is the largest source of nutrients to Lake Erie on the Canadian side. And when you move up to Canada and work on water quality, issues of phosphorus are on everybody's lips. And so I started to think more about phosphorus. I got some pushback on that, saying you're a nitrogen person, you can't work on phosphorus. But I think those of us who work in this area know that you can't, if you're managing for water quality, you can't think about nitrogen and phosphorus separately. If you're modeling, you can't think about nitrogen and phosphorus separately. So I got on the phosphorus path here, and phosphorus is an issue in a lot of the big Great Lakes, smaller lakes in Canada as well. I'll give you an example of why I started thinking about the legacy issue. This is a headline from a news story that came out 2017. So that's about 8 years ago, September 17th, 2017. Look at this headline here. 5-year fight removes less than 1% of phosphorus from Lake Winnipeg Basin here. After spending $18 million, we're not seeing decreases in phosphorus. In this article, there's an interview with the executive director of the Lake Winnipeg Foundation, and she says, I've got highlighted here, it's surprising. I had to read that line in the report a couple of times because we're talking about 5 years of effort. and achieving this reduction of less than 1%. And, the question is why, and this is where we start to think about how this legacy buildup that Andrew was describing so eloquently starts to affect water quality in the long term. I wanted to give us a little bit of an update here. I got some numbers from 2023 for us to look at. So 6 years after that original article that I showed you here, and we still don't see any appreciable improvements in those phosphorus loads, even though there continues to be very intensive action in the Lake Winnipeg Basin. And I like to say, this is a lot like going on a diet and never losing any weight. It's frustrating and you give up. And particularly when this isn't just a theoretical concern. We've got people boots on the ground, getting farmers and landowners, any number of different producers involved in these conservation efforts, implementing best management practices. But when you can't show a positive outcome, and you can't really explain why in a easily communicated way, it's frustrating and it's hard to keep these efforts and the money for these efforts moving. And I think that's why I've become so committed to working on these legacy nutrient issues. So if we go back to the hypothesis, or the basic hypothesis around the legacy nutrient problem, it's that in these intensively managed watersheds where we've got a lot of ag going on, crop production, intensive livestock production, and in many areas, rising population as well. You have legacy stores of nutrients that can build up over decades of these management practices, and that these legacies aren't just sitting in the soil and our water bodies long term. They're sitting there, but they're also serving as a source, and they're making it very difficult to achieve improvements in water quality. So our basic question when we're trying to get these water quality improvements is, how long is it going to take for water quality to improve in the face of these legacy problems here? And when you're trying to answer those questions, you have to think about a couple of different things. And Andrew got at a lot of these quantification issues in his talk. We have to think about what are the stores of these legacy nutrients. Here we're talking specifically about phosphorus in our watershed. How much is there? What form is it in when it's there? Where is it located in the watershed? And then beyond those stores, beyond the how much, is how fast? What are the depletion rates? How long will it take those excess nutrients to make their way to nearby water bodies? So to think about answering those questions, we also have the complication of thinking about changing climate as well, because the kinds of weather patterns that we're seeing now are not the same as those that we saw 20 years ago. They're not the same as what we'll be seeing 20, 30 years from now. Not just in terms of temperature, but of course, water fluxes. We've got a higher incidence of high rainfall, flood events, drought events. How are those climate complications going to impact the fluxes of legacy nutrients? So in today's talk, I'm going to just talk about this from like two ends of the dog, I guess. One, thinking about the mass balance side of things, and how can we start to think about these stores of legacy nutrients at a macro scale? How can we reduce the uncertainties in those values that we're predicting in those mass balances? And then I will also talk more about the modeling side of things, looking at can we better create models to capture legacy accumulation and depletion dynamics so that we can better predict these water quality trajectories as we're putting so much money and effort into improving our management practices. So I'm going to kind of rest on this slide here a little bit and talk about a data set that's being developed out of my group called Trend Phosphorus. Trend is an acronym. I don't have the whole name for it here. I believe it's Trajectories of Long-Term Nutrient Dynamics. And the idea is to put together mass balances like what was described to us by Andrew across the US. We're also working on Canadian versions of these data sets. And as an aside here, I'll say I'm part of leadership right now on a North American nutrient budgeting work group. And this, I know you mentioned some work by Robert Sabo. Robert Sabo and Janet Compton at EPA are also part of the leadership on that group. We're working with Dennis Swaney and Bob Howarth, who have been really instrumental in working on the net anthropogenic phosphorus input data sets. Rebecca Munich, who's here, is a part of our group as well. And one of the big goals of this group is to say, let's take all of the people working on this kind of mass balance group, bring them together and talk really seriously about how we can be more consistent with the development of these data sets, how we can reduce uncertainties and do the kind of boots on the ground work needed to validate or improve the parameterization of these data sets. So I think that's a really important effort that's going on now at a North American scale. We've got great Canadian colleagues involved with this as well. But back to our trend phosphorus data set, I would say one of the things that is unique about this data set is one, not that it's national scale, but that it's national scale over the long term. It's a data set that goes from 1930 to the present with the idea that we need these long-term sets of input and flux data to really address the legacy phosphorus issue, because it's not just a matter of what we're doing in terms of inputs and management today or in the last 5 years, but getting that long-term trajectory, like Andrew was showing for the Illinois watersheds. That's important. Another thing that we're doing with this data set is that we're taking data that's generally available at a county scale, and we're using a number of different approaches to downscale that to both 250 meter grid scale and even 30 meter grid scale to better support modeling efforts. But broadly, I'll say I just want to talk about some things that these kinds of data sets can give us. Here I've got results, which I know the maps are a little bit small here, that show different fluxes in our phosphorus mass balance over time and at a 250 meter grid scale across the US. So we can look at where's the phosphorus removal in crops? Where is that concentrated? We can look at spatial patterns in fertilizer input, in livestock manure inputs. So we can look at those spatial differences across the country. We can also look at trends over time, which you can see for those three components of our mass balance in the lower plots there. And one of the things I think is interesting about those plots is it's not representing the shaded bands are not representing uncertainty. They're representing the range of values at points across the entire country. So one of the things that's interesting to me, let's take a look at the manure plot as an example. If you look at the dark purple line in that time series, what it shows is that phosphorus inputs across the US from manure have stayed pretty static over the last decades since 1930. But then if you look at that band of values across the country, what that represents is the incredible intensification of livestock production, and that we're now seeing counties and areas of the country where the inputs are incredibly high or have gotten lower. So in the mean, we're seeing pretty static phosphorus inputs, but from a spatially distributed perspective, we're seeing incredibly large increases in those phosphorus inputs in some areas, and that just really reflects that intensification of agriculture and how we have to think about where those phosphorus inputs are. We can also pull other kinds of metrics from this mass balance data, looking at our overall phosphorus surplus. That's the difference between the inputs that are going into the landscape and what's being removed through crop uptake, crop production. And we can look at both spatial variations and surplus values, and also that temporal, that time series. We also can look at phosphorus use efficiencies and how those are changing over time. So you can see quite a bit of difference between those use efficiencies in 1980, where phosphorus use efficiency was typically quite low, especially across the Corn Belt area. And then by 2017, we see phosphorus use efficiency changing, and because we're increasing those inputs and doing a lot of mining of soil, as you showed for some areas of Illinois in your Illinois scale data. So these are the kinds of things we can think about, how to use these mass balances. I completely agree with you, Andrew. There's certainly limitations. If we say this is our cumulative phosphorus surplus in this area, is that our legacy phosphorus? Is that's going to absolutely determine what we're seeing in terms of in the soil or what's running off into waterways? No, things become more complex there. And there's a lot of improvements to be made, but I would argue this gives us a very good framework for understanding phosphorus fluxes at these large scales. And it gives us kind of bounds in understanding at most what might be there. But to really make a lot of progress beyond that, I think we have to go beyond to the mass balance. And I think here is, I really loved the plot that Andrew showed with the different approaches to quantifying phosphorus legacy. And we had our big gray area, right? And I think a lot of the modeling approaches that are being developed right now are what I think can help us move into that gray area and get better at the predictions that we're making here. So I'm going to talk specifically to you about some, again, modeling efforts in my group and what kinds of things those phosphorus models can tell us. So we have created the element phosphorus model, and it's designed to explicitly be able to account for accumulation of phosphorus and depletion of legacy stores. It's built on a previous legacy model that our group developed, the element nitrogen model, which we've used to model a wide variety of watersheds. Uh, One that we've spent a lot of time talking about is just legacy nitrogen dynamics in the Gulf of Mexico, where we showed that legacy effects there show that even if we were to become completely efficient with our use of nitrogen in agriculture in the Gulf of Mexico, that it could still take up to 30 years to meet the kind of goals that we have for the Gulf of Mexico. So we've taken this legacy nitrogen model, the element model, and adapted it and made it bigger and better to account for phosphorus fluxes as well. So I won't go into all of the nitty-gritty of the model here, but just to say that it has different components here. We're able to look at, as you see on the left here, modeling of phosphorus dynamics in the soil, looking at surplus going in. We use the kind of mass balance data to estimate surplus phosphorus going to the landscape. We then look at runoff from the landscape. We look at wastewater effluent coming in. We also explicitly model groundwater fluxes and look at a range of travel times to the to nearby rivers to really try to get at what are those time lags due to accumulation of legacy both in soil, in waterways, and in groundwater, with the goal of trying to predict what are the time lags that we would see to achieve water quality improvements. And I'm going to walk you through, I mentioned the Grand River watershed in Canada here. I'm going to walk you through just one of the modeling exercises we've done with this model to show you what we can learn here. So the Grand River is an example of one of those watersheds I talked about where we have pretty intensive agriculture here. We also have growing populations here. So you have pressures from both agriculture and urban areas in terms of phosphorus fluxes to the river and downstream lakes here. You can see just what the long-term trajectory has been for both agriculture and population in this watershed here in this plot. You can see that we've had actually a reduction in agricultural area over the decades, but pretty massive in increases in population density. So let's go to some pieces of the model and what it can tell us. It's explicitly allowing us first to look at domestic phosphorus sources. So this is phosphorus coming from human waste that would go through the wastewater treatment plant. We're also explicitly accounting for detergent phosphorus, which has certainly reduced in magnitude since the 70s when we started seeing detergent bans, but is still a factor in what we see going to the wastewater treatment plants. And through the modeling, we can see what is the magnitude of phosphorus loading from these domestic sources to the river. And I love this set of results because I see this is a success story, right? This shows how upgrades to wastewater treatment plants and management of detergent phosphorus really dramatically reduced what was going to the rivers here. This is our more point source effect. Here in our legacy phosphorus section, we're saying, yeah, but what about those landscape sources, those non-point sources? Well, let's go to what we see here. In the mean, this is our watershed phosphorus mass balance representation that we get from using that gridded input data that I showed you from the trend data set, and then aggregated using the model. We can see as represented in that dashed line here that the phosphorus surplus peaked late in the 70s, early 80s, and has decreased since then and started to stabilize. And you can see, you know, those various pieces of the mass balance there. Next, we use the model to actually predict the phosphorus fluxes to the river here for the Grand River. And the model does a pretty great job of getting those annual phosphorus fluxes. You can see here the dashed line represents our modeled fluxes here. The red line is just a long-term moving average, and those red diamonds represent the actual measured phosphorus loads. So you can see the model is doing a pretty good job of capturing what we're losing from the landscape to the river. So the question is, where do we go from there? What do we learn about where we still have legacy issues in the watershed? And we know we've got them here because look at where that baseline line is, that green dotted line at the bottom there. We can see, though we've made improvements in point sources, we've implemented a lot of management practices to reduce phosphorus runoff from the agricultural areas, but we still are not getting back to those baseline levels. So let's take a look at where the accumulation is happening across the watershed. Well, first we can see that according to our model, we're seeing a large accumulation in soils. So this isn't just, and I guess this again is going back to your point that the you can't just use the mass balance itself to get this. And here we're using a more process-based approach to look at what's accumulating in soil. The model still tells us there's very significant accumulation. We see accumulation in groundwater. We see a very large amount in reservoirs and riparian zones. On the other hand, we see that since 1900, only about 4% of those net phosphorus inputs to the watershed have been exported to downstream water. So again, that's our legacy effect. That's where we're showing accumulation there. So if I'm trying to stay within our time period here, but we go back to asking, how long is it going to take for water quality to improve? We're looking for a 40% reduction in total phosphorus to Lake Erie here. Our model can show us those time periods that it can take here. I think I'm going to focus on two different scenarios here. Just the first, which is our business as usual scenario. If we keep doing what we're doing, here's our legacy effect again. If we keep doing what we're doing, our model shows we're actually going to keep increasing our phosphorus levels, even though we've really reduced our inputs. And that's because we keep seeing depletion of those legacy stores. Of course, there are interventions that we can put in. I'll just draw your attention to the long-term simulation we did here with very aggressive interventions. And that again shows our legacy effect. Over a 1,000-year period of the model, we show we can return to baseline in the year 2402. So, certainly not with any kind of policy time period for management. So these are big issues we're working on. So I am going to stop there. We may have time for a question, but looking forward to talking to you guys more about this.
Thanks so much, Kim. We want to be very inclusive at this event, so I wonder if your dog has any questions. How much phosphorus is in the treats, or
She's pretty bored with it.
She's seen it before.
She's seen it all before.
Okay. Any questions? Man.
Yeah.
Hi, thanks. Great presentation. I was curious, like when you're projecting out 20, 30, 40 years, it's really challenging I would imagine, from like a calibration or validation perspective. And just, do you have any thoughts on that? Have you developed any interesting ways to like try to validate the models or assess the uncertainties?
So the model validation part comes in terms of the period where we're at now. Of course, we'll calibrate from one period, validate on another period, and say, are we doing a pretty good job of predicting, and particularly predicting changes over large changes in management, to see, are we capturing the things that are important here. I'd certainly say when you're, even, 30, 40 years, if I'm projecting 1,000 years into the future, that's pretty tough. We're not running all of the climate scenarios over those long-term periods. So there's definitely uncertainties in those areas. But I would say it's more looking retrospectively. Is the model able to do a good job of predicting over changes in management over longer time periods? And we feel pretty good about that. Yeah.
The original news clipping with, in 5 years you had a 1% drop. I mean, was there like a huge amount of money spent, or I don't understand what the outrage is. That doesn't seem like a horrible thing for a landscape scale.
Oh, well, I kind of laughed when I saw that initially because again, I do quite a bit of work in the Chesapeake watershed or in the Mississippi, where we've been working for decades doing these things. So 5 years seems like a very small time period to expect a lot of change within. But again, if I would say on the smaller scale, again, when you've got a group of landowners in a watershed who have agreed to do X, Y, and Z to improve outcomes, and then they don't see it, 5 years seems like a long time. And again, when we think about policy planning cycles. I'm not a policy person, but we think about it in terms of election cycles, and it's hard to say, I'm gonna run on reducing phosphorus runoff to Lake Winnipeg, and I have a term of 4 years, but guys, don't expect to see any results for the next 20 years. It's difficult, I think, and people want to see good, fast results. But I agree with you. I don't think it's I don't think it's an outrage, but that's the kind of discussion around the issue.
So the real takeaway is stop pooping. I mean, that would fix it faster.
That would fix it. And I like to say, the reason I think doing these models to give these predictions for timescales of recovery is that you have to give people reasonable expectations. And that's exactly what you're saying. It's not unreasonable that we've only seen a 1% drop. But if you don't have that context for understanding, the disappointment and frustration can be there. So that's why I think this modeling work can be important.
Really enjoyed your presentation. I'm Vinayak Shirikar from Ohio State. When we're looking at the models, one of the important parameters that goes in that is initializing the model at the right soil test phosphorus levels. I was curious, what was your source of data? How were you able to get down to the farm scales for the
so we did I guess one thing that Andrew brought up in his talk was using chronosequences to try to understand, and we worked on getting soil data that was adjacent to agricultural zones where we might be able to. I know Mark David did some work in Illinois where he had soil nitrogen, carbon, phosphorus levels in agricultural fields, and then there were ditches or cemeteries nearby, and he did testing of soils there to get comparison. And we tried to use that approach to do that kind of initialization.
Initializing the model with the exact same STP for all soils, or have different?
We have different values based on soil maps. Yeah.
Thank you for showing a successful transfer from A to P. I appreciate that. So I have a question. You had one slide that showed the PU's efficiency changes from 1980 to 2017.
Yes.
So what are the major contributors to that improvement?
It kind of depends by area. There's some areas where, for example, livestock production has moved away from a particular area, so the inputs have reduced in that area. Some of it is just due to changes in cropping patterns there. And I would say particularly around the Great Lakes area, I see real reductions in the fertilizer use there. So I think that's more of a very concerted management outcome.
Yeah. There, I'm Ryan with Coke. Do you mind just maybe restating some of the sensitivities within the model based on how resilient some of the legacy stored P is there? Because if you were to wave a magic wand, I'm curious of which of those parameters you could effectively change within a reasonable period of time to make a dramatic increase.
Oh, so you're talking about those outcomes. Those
yeah, the sensitivity and the parameters in the model. If you were to just move the levers, where's
and I would say I hesitate to say this in a gathering where we're so interested in improving agricultural management and improving fertilizer management, but essentially nothing we did with the model in changing fertilizer inputs really significantly changed those outputs. Whereas changes in livestock densities or livestock management, the watershed phosphorus loads were quite sensitive to changes in livestock there. And of course, tweaking any kind of point source makes a more immediate difference as well. That's no surprise.
One more question, then coffee.
So that brings up a point. I was looking at this slide earlier, and it seems to almost completely replicate a paper that Pete Bottas did using Apple for Maryland.
Okay.
Same results,
Yeah,
right? But they took into account initial soil test P. So it's kind of the same question that I posed for Andrew. Do you take where you say ag P surplus? Is that just in or out, or is it in, out, and soil contribution to crop yield?
It's it is not taking into account that soil.
That's pretty impressive, because then your ag P surplus is just input versus crop removal.
Yes. Yeah.
Okay. Apple came up with the same results, but it took into account soil phosphorus concentration. So we basically gridded out the state by binning soil tests into agronomic categories.
Okay. Interesting. I want to go back to your question. One other thing that I think is not, you don't see it so much in these scenarios, but you see it in this slide, which I kind of slid over a little bit. I think this is an incredibly significant finding, is how much of that surplus that enters the river network ends up in reservoirs and riparian zones along the way. And much of a lot of my current work is kind of pushing on that a little bit. Are there ways that we can think about managing reservoirs for water quality to keep that phosphorus from going downstream, or to look at the seasonal dynamics of that phosphorus release?
Thanks so much, Kim. Round of applause, and then we go have coffee.
Thanks, everybody.
So a bit of a heads up on the plan for what's left of the session. We're going to be having one more speaker, and then we'll be having two panelists who live in the world of policy. So the setup here is 3 talks on the science, what we see as gaps, and then we'll have a open panel discussion on what do we do about that? How do we manage these uncertainties, and how do we try to manage legacy phosphorus? So the next speaker is Dr. Django Bada. He's an associate professor at the University of Florida Soil, Water, and Ecosystem Sciences Department in the Everglades Research and Education Center in Belglade, Florida, South Florida. Then, excellent. His research and extension program deals with promoting sustainable ag by integrating soils, water quality, nutrient management in South Florida and beyond. Alrighty, so we now have a panel. A few thoughts or a few words to prime this panel discussion. So we've heard quite a bit today about agricultural legacy P sources. One point that might be good for us to think about is expanding that discussion to non-agricultural sources as well. Things like stream bank erosion or these legacy sediments, as we're seeing in these photos from all the ditching, those might be good to include in the discussion on policy, which considers all sources of phosphorus loss. So on the panel, new members here are Lauren Lurkins from Lurkins Strategies, and also a member of the Agricultural Nutrient Policy Coalition, ANPC. ANPC is a coalition of over 50 state and federal ag trade associations and businesses focused on supporting U.S. ag in its efforts to protect water quality. We also have from Illinois, Trevor Sample, from the state EPA and a member of the Federal Gulf Hypoxia Task Force. Trevor has worked on watershed issues at the IEPA for 23 years and currently serves as the agency coordinator for the Illinois Nutrient Loss Reduction Strategy. He was raised on a farm in central Illinois and has a bachelor's in agronomy from Illinois State. So the goal for this panel, which consists of 2 of our researchers and 2 of our policy centric members, is I would propose to start off perhaps on your first impressions, and then if we could maybe guide discussion towards what about other non-ag legacy P sources when making policy. So who would like to start?
Can you hear me? Okay. Yeah. Okay, it's on. So hi everybody, I'm Lauren. I know some of you. Thanks, Andrew, for the intro. I live in Illinois, and Andrew and I have worked together for a number of years. I have my own consulting firm now, and one of my clients is the Ag Nutrient Policy Council. Like Andrew said, it's about 50 states and national ag groups. So that's state farm bureaus, national farm bureaus, commodity groups, and agribusiness. So we've got several of the fertilizer companies that are a part of our effort, as well as their state associations. So we have worked since 2010 to be able to productively engage ag in these conversations at the national level and also across the country as different either state governments or otherwise are working on strategies to reduce nutrient loss. Obviously, and before this time, I spent about 10 years at the Illinois Farm Bureau, and I worked every day with farmers. So I was talking with one last night. He really likes Andrew, so he said to tell you hi. I'll tell you that it is later. Everybody loves Andrew in Illinois. And, a lot of these conversations, much like all of you, if you work, day in, day out with farmers, they're kind of burned in the back of your brain. And Josh and I were talking about this. There's a lot of things I can't remember, but there's other things that do. And, I always think about farmers individually when we hear conversations about this. So when I worked at Farm Bureau, and I think even in my role now, I always sort of straddled that line between the real world on the farm and then the world that Trevor and our folks in agencies work in. And that would also include partnering with academics to be able to bridge that gap. But I think the thing that strikes me the most is actually the conversation about 1,000 years. Obviously in policy, whether it's governors or state lawmakers or members of Congress, they don't think about 1,000 years. And I think about this issue largely as a people issue. Yes, we need scientists certainly to be there helping people understand it, but we also need people to be working together. Different sectors actually coming together and listening to the same science and working together. And that sounds sort of like Pollyanna-ish, but it actually is pretty important. Trevor and I worked together on the Illinois strategy, and it started very negative across these stakeholders in the beginning, probably 13 years ago. And by him essentially forcing us to all come into the room over and over again, we created partnerships where we would then spend our own money to work with each other. And I guess my biggest thing is I just hope that people get fatigued on this issue, especially when they don't get any credit for any, movement forward. Farmers will get burned out. Their staff will get burned out. Even agencies will move on to other things. And so I guess I just want to always encourage people to continue to keep working on this issue. Obviously, more issues will come, but just kind of staying dedicated and not getting worn out. Because I think the worst thing that can happen is when people retreat to their own corners and then they start working on talking points and media pitches, and then we're further apart on finding the solution. So it bums me out, honestly, to hear how long that will take, but it is, and we've talked about this in the ag policy world, is like setting reasonable expectations for everybody, for your policymakers, for government agencies that fund certain things, and for individual farmers that day in and day out have to keep making these same decisions to keep going on that BMP or a set of BMPs on the farm that makes sense. So I just don't want it to get to the point where people start pointing fingers and then we lose all of the progress. So, but I guess the thing that sticks out to me is just reasonable expectations and making sure that people have the support to keep coming back together.
Thank you, Lauren. Trevor, perhaps a few words, or I think Kim may have a response or thoughts on Lauren's points.
I have just a quick response. Is one, you use, I'm gonna pick up on two things you said. One is that I bummed you out. And two, you use the word solutions. And I have to say, just like everybody apparently loves you in Illinois, everybody always says to me, you're so depressing when I give a talk, because I talk about these timescales for recovering them longer than we want to hear. And I just want to say, I think it's important to set reasonable expectations, not as a downer, but for providing a context within which we work. And two, I would say it's important to get started now. If it takes a long time, that's okay. We need to act now. And three, I think instead of working in a space of continually talking about the problems, I think the solution idea is important. And I would say, when we have this context of understanding the problem, we can really start to effectively think about solutions. It's one of the reasons why I've moved in my work to really thinking a lot about wetlands and the role that they can play in capturing legacy phosphorus and really making giving us more short-term successes and water quality improvements. So I think working in a solution space is important.
Trevor Sampo, Nutrient Loss Reduction Strategy Coordinator for Illinois. I've been the coordinator since 2017, but I started working on the strategy back in the beginning when the first, what we call the Stoner memo came out in 2011, directing states to implement strategies, which was really USDPA's way of saying they're not going to, it's not going to be top down USDPA telling states how you're going to reduce nutrients. It gave the states the chance to work on their own nutrients for their own unique situations for each state and how they're set up. So we started working on this in 2011. We put together our science assessment team, started working on our science assessment, which was the basis for our strategy back in 2013. Some folks I've seen him give a presentation have cited Dr. Mark David, and he was one of our principal investigators on writing our strategy. And at the time, legacy phosphorus wasn't a term I don't think you'll find anywhere in our strategy. We put that science assessment together in about a year and then spent about another year writing the rest of the strategy for how each sector is going to reduce their phosphorus and nitrogen. And so we didn't have a lot of time to, I mean, we took what research was available at the time and put that into our science assessment. And so when you look at we have some pie charts that show the percent contribution that we estimated per sector for agriculture, point sources, and urban stormwater. And when it came to phosphorus, it was about half and half for agriculture or non-point source, and point source and a little bit from urban stormwater. But we even knew at the time that wasn't quite right. We were pinning all of the non-point source onto agriculture. We know that there's other sources as well. It's just 75% of Illinois' agriculture. So that's where when you get runoff from a statewide perspective, most of it's coming off of ag land. Part of the pieces that we knew existed, but we didn't have quantified, was stream bank erosion. And that's something Dr. Martin's been working on for a couple of years now. Hopefully, maybe by next year, we'll have an estimate on the amount of statewide contribution from stream bank erosion. Iowa came out with that last year before last, and they said it was about 31%. We're using a little more in-depth methodology. I think Andrew will argue, try to come up with our number. As we split that pie into better pieces, so we're not attributing all of it to agriculture, especially we see the work that Andrew's done showing that over the last 30 years, ag, from a mass balance perspective, cropland has been negative. Not to say we're not still losing something off of certain aspects in certain fields or parts of fields where we have high phosphorus or we have high erosion or we have large storm events. So it can move around the state depending on where your hotspots are, depending on precipitation or storms any given year. But it's important to know where the phosphorus is coming from so we're properly addressing what BMPs go where and how much we need and not pinning it all on agriculture, knowing that agriculture still definitely has a role, or other reasons of just keeping soil erosion in place, improving soil health. A lot of the same practices that sequester carbon, improve soil health, reduce nutrient losses are the same practices to cover crops and reduce tillage and nutrient management plan. So the talk about legacy phosphorus, we think of it in two different ways. The most common way we talk about today is just legacy phosphorus is in the field. But we also have this legacy phosphorus that's also in the stream system after 100+ years of erosion. First broke up the prairie, draining the wetlands, and we start having deposition and knowing how long it takes that phosphorus to work its way all through the system. You think of Chicago River starting in Chicago and making it all the way down to north of St. Louis, how long it takes that phosphorus to move through the system as it gets picked up and deposited, and how much do we have sitting in the stream system? How thick is it? How wide is it? How much sediment we have sitting there and what the concentration is? We don't have a lot of data telling us that. And if that legacy phosphorus is contributing to the problem with each rain event, it'd be nice to be able to quantify that so we know how much is in there. And then also we start talking about then lag effects. of how long it's going to take to flush that out of the system. Even if we could wave a magic wand and put every practice on every acre that's needed, how long is it going to take to flush that out? Have realistic expectations. Right now, when we developed our strategy in Illinois, we had interim goals of by 2025 to reduce nitrate by 15% and total phosphorus by 25%. Now, the water year 25 ends at the end here in a couple of weeks, so it'll take USGS about a year to crunch the data and clean up their data. We do have a continuous monitoring network in place. We have 8 gauges on our major rivers, and so they're able to take that data. It's continuous data, so they're able to take that, and we have a pretty good handle on how much nutrients we're losing for nitrogen and phosphorus in any given year on an annual basis, and we can follow that 5-year. So we know what we're losing. But it comes down to then how much of that, where that's coming from and what we can do about it. And we start talking about lag effects and timing. So we have our interim goals, but for a state, we never set a long-term goal. We just said we'll eventually meet 45% reduction. Now, the Gulf Hypoxia Action Plan wants to meet the Gulf goals by 2035, a 45% reduction. So we have to start talking about what's realistic expectations. I was thinking maybe decades, but after hearing what I heard this morning, now we're talking about centuries, thousands of years. So the realistic expectations that, I think all we can do is look at our scenarios that we've built in our state, say about how much the practices do we need to reduce the loads from point sources, urban stormwater, and agriculture, and still go by that. Know that we have to do everything we can on the land, show that we're doing everything we can on the land. If we still have large losses after that, we can say we've done everything we can from an anthropogenic source. In terms of point sources, just this past year in 2024, we did meet our 45% reduction. We've had some of our larger Chicago dischargers that discharge hundreds of millions of gallons a day are now meeting permit limits. And so last year we just did get a 46% reduction from our 2011 baseline. So we've reduced phosphorus load for point sources in that time span by about 9 million pounds a year. So again, we know it's not the point sources are contributing. Someone showed the graph earlier in Illinois where the 5-year average up through 2021 was showing 30% increase in phosphorus loads from the 80 to 96 baseline that everybody used. So I think it's important to acknowledge legacy phosphorus exists at the source, and also being realistic with how long it's going to take to work that through the system. Being mindful, we still need to do what we have to do in the watershed, but there's still these other sources out there, and how do we deal with those? And right now, I'd like to quantify how much that might be. That's going to take some time and effort. Money as always to figure that out.
So apart from money and time, I want to ask about patience and flexibility here. For the panel, what are your thoughts as researchers and policymakers on how do you communicate, hey, there's something that we may have missed, legacy P, and oh yeah, we're not really sure about details, and it also might take 1,000 years. How do you do that, not lose face or lose the trust of stakeholders if they say, how could you have missed that? Any thoughts on how to strategically integrate this emerging science without turning off a lot of the people?
I'll start, I guess, my days are messed up now, but a couple days ago, I was in a meeting with actually his acting director, and it came up, we were, meeting with a soybean association at that point, and his acting director, who I really like, says, that I am working on figuring out how to address non-ag, non-point source for the nutrient strategy. And I sort of just chuckled, under my breath, like, oh, that's awesome, that he's talking about that, but he thought it was on his shoulders to figure that out. So he calls, Region 5 EPA to say, I need the answer here, and I need it pretty soon. What are we going to do about this? And I said, oh my gosh, well, I'm actually going down to this meeting in North Carolina where all these scientists across the country are really working to figure that out. Trevor's going to be there, others, but it's I do think sometimes they're unaware of conversations like this. And that it shouldn't just be on the shoulders of, a agency director at the state level to figure it all out. So on one hand, I think he felt relief that it wasn't on his shoulders and it wasn't just Illinois EPA trying to figure it out, but there are other people, you know, in the country really trying to wrestle with that. But again, I think if stakeholders ask them a question or if a governor's office asks questions, they're going to want quick answers and can't say, oh, I know that, you know, there's scientists somewhere working on that. We have to be able to show progress even in the scientific discovery and what you all are finding. So no pressure, but there's somebody waiting for some answers in Illinois.
Yeah, and it's not just on our agency. We implement the strategy side by side with our Illinois Department of Agriculture. So our steering committee, the way we're structured, is our agency, Department of Agriculture, and then Illinois University of Illinois Extension folks work day to day on both helping with tracking and reporting and meeting facilitation. We have a policy working group made up of close to 30 different organizations, from agriculture to stormwater to drinking water, environmental groups. Everybody's at the table. And they've been at the table since the beginning. That's so we drafted our strategy. We didn't just write it up, put it out for public comment. It was a very public process to develop our strategy, where we had constant meetings informing everyone along the step of the way, getting input from them along the step of the way. So we had a lot of buy-in when the strategy came out by all the organizations. They already had their say and had the discussions and came to agreements on what we wanted to have in our strategy. So everybody's kind of on the same page when it's released. And so we work hand in hand with our Department of Agriculture strategy. It's not just one agency, and it's not just our agencies, it's all of the working group folks, all of the commodity organizations, ag organizations, conservation groups, point sources. We're all working together on this. So we don't just have the policy working group, we have an ag group and urban stormwater groups and communications group and benchmark group. We have like 9 different subgroups that meet throughout the year. And that's part of what Extension helps set up meetings, plan agendas, get the presentations, get speakers lined up. So we're constantly talking about this. It's not just a strategy we develop and kind of walk away. We come out with biannual reports every 2 years that show the progress that we're making, or trying to quantify the practices that are implemented, the point source reductions that we're seeing, urban stormwater efforts, and the water quality results from USGS. So we come out those every 2 years. So we've always viewed the strategy as a living document. You always have a section in those biannual reports to update the science assessment. So any new research we think is really relevant, we include that. So we're always updating and informing folks. So legacy phosphorus is just another way, as long as we're having Andrew and those types of researchers come and talk to our policy working group. We have an annual conference. It's coming up November 5th. So we have annual conferences. We usually have anywhere from 100, 125 participants come to that each year. So yeah, as new emerging issues come up, we try to stay on top of it and let everyone know what the newest issues are and what the newest research is showing. So that's, I think, how we lay that to all of the stakeholders and all the groups that are working on this in the public, by having presentations and getting that information out there.
I will say too, I was going to add on the living document that I think your question was like, how do you talk about this new aspect without, you know, breaking trust, or, you know, well, you said it was this. It's like from the very beginning, we knew that we should be continuing to learn more, not just about the practices, but about the bigger context. And it's not just Mississippi River Basin states that have these nutrient strategies now. There's about 30 states across the country that are following this path. And, you know, you want to keep it open-minded where we're all continuously learning a little bit more. And I think that that's kind of the whole point, right? Is that we're not all stuck to that list of what we knew about practices back in 2013 or even 2010 in our cases. Now, where you don't have that flexibility is when things are locked in regulation. And, you know, like the Florida example, you know, it is in law where, you know, here's your goal and here are your list of practices. We actually have the flexibility, you know, in other parts of the country right now to keep that innovation and to keep that sort of learning happening and informing farmer decisions and point source decisions. Sorry to cut you off again.
I think Kim had some points here. This is great discussion.
Yeah, I was going to say, in my experience, I see people being receptive to the idea of legacy, and I think there's something fairly intuitive about it. That we've been doing these things for years. Of course, there's going to be long-term effects. But what I come up against a lot is a fear from the more environmentalist side saying this legacy idea is going to be used as an excuse for not doing anything. And there certainly are cases you can point to where that's happening. Des Moines, Iowa, for example, famously had a court case a few years back related to high nitrogen levels, and they were trying to hold the upstream drainage districts accountable for millions of dollars they were having to spend on water treatment for the city. And some of the reactions was that, well, this doesn't have anything to do with what we're doing right now. People, this is a legacy effect. So don't blame us. Don't hold us accountable for this. So I think those things can happen. For me, I think what's important to saying that these are legacy issues, that legacy phosphorus is an issue, isn't an excuse for doing nothing right now. It's maybe an opportunity for us to say, no, this is what we should be focusing on to address these legacy issues. So that's my take on that.
I'll second everything Trevor said as far as communication. I really think that having those communications between different stakeholder groups so that we all are on the same page. We may not agree, but we at least have heard each other out. That's important. The other thing I wanted to point out was last week we were at my first time to the Corn Belt and graciously toured some of the corn soybean area. And I learned about the checkoff process. Now, maybe some of you all locally are aware of it, about the checkoff, but it's basically checkoff funds are, and correct me if I'm wrong, that the industry is putting back into the public sphere to address some of these issues. And it is calculated at a percent of 0.5% of a bushel. It's a calculated amount, but every year there is some funds that go back into research and topics that have nothing to do with yields. They do not want to see topics that increase their bottom line. They want to see topics where maybe legacy phosphorus, maybe nutrient use efficiency, maybe discharge reduction. Florida has a similar rule. And so in the last 3 decades, they have been charging a dollar amount per acreage that goes into the BMP program to evaluate some of these practices. So the growers are actually putting that dollar on the table each year to do that. And I think these are some of the highlights that if we can use these initiatives to bring the legacy topic up front, then we've got a win-win situation here.
So I'll just say in Illinois, besides the commodity checkoffs, we also have our Nutrient Research and Education Council that was established in 2012 by state law that takes a fertilizer assessment for every ton of fertilizer sold, regardless of whether it's agriculture, lawn fertilizer, or whatever. Any fertilizer sold was assessed $1 per ton, and 25 cents of that went to the Department of Agriculture for their fertilizer inspection program, and the other 75 cents went to this Nutrient Research Education Council. Before we had something called the Fertilizer Research Education Council, but it kept getting swept. The funds kept getting swept and not being used for what they intended to. So this law made sure that this funding was dedicated to the council to use for research for nutrients of water quality. And we recently just passed to increase that to $1.25. So now the council gets $1 per ton. So that'll give us close to a little over $4 million a year. Before that, we had about $3.5 or so million a year that we'd spend on research since 2012, looking at all the practices, combinations of practices that universities research to show that the practices that we're recommending in our strategy do work and what their performances are. Do they phosphorus by 10% or 50%? Same with nitrogen. So we feel like all the practices that we recommend are soundly based in science because of the research that comes out of the internet.
Excellent.
This is a good time, I think, for the audience to ask any questions of the panel members.
So I'd like to strike a more optimistic tone because everyone kept saying 1,000, but Kim, if I understood your slide right, in about 25 years, you could get that 41% reduction if you just went to balance. 25, 30 years, something like
Yeah,
that.
it was more the multi-century outcome if you wanted to go back to that baseline level, which
Sure.
I don't think is anybody's
Can't do that,
set
right?
of
Yeah.
goals right
So
now.
so we ran some similar simulations. Pete, I think, emailed you when I said in your slide. So that you could hit in the Chesapeake Bay 47% reduction. And we actually were a little bit more conservative than you. We just said if your soil test is over 75, you stop applying, right? And we don't expect any yield increase from phosphorus if your soil test is over 30. So we were still allowing some maintenance, right? So I started grad school in 1998. The Water Quality Improvement Act was passed in Maryland and Delaware. And I was working in the Chesapeake Bay region. And if in that year they had just said over 75, stop applying phosphorus, and we're going to take all the dollars that paid for Josh and everyone else to work on phosphorus for the next 25 years and just shipped it to Iowa, according to our modeling, we would have met our goals. We'd be done and working on something else today. So I would say this is totally feasible, right? And to the optimistic point of solutions, I just spoke to the Maryland Grain Board recently. And, I think the solutions that we know what we need to do, right? Stop building and yield, and yield, right? That's the solution to legacy phosphorus. So that's going to be our approach in my program at the ARS is pushing yields to address legacy phosphorus. So anyway, I'd say that's an optimistic take that like if in 1998 we had just stopped applying on high P soils, we'd be done. Of course, none of us would have had jobs now because we would have used all that money to ship phosphorus. But
Can you elaborate that on the yields?
yeah, so just real quickly on the yields, so yield drawdown faster,
Or yield
steeper drawdown.
steeper drawdown?
Right.
Farmers want that BMP added to the list.
Yeah, so that's what we were talking about.
Yeah.
That's what we're pushing for.
So I'm glad you brought up the Chesapeake Bay because it also brings us back to something that we've talked about on the panel, which is the legacy within the stream network. And there's some very interesting work in the Chesapeake Bay on the Susquehanna River. So the Susquehanna is the biggest watershed draining into the Chesapeake Bay, so the largest source of phosphorus and nitrogen. And there's a very large reservoir, the Conowingo Reservoir, right at the mouth of the river before those nutrients are put into the bay. And so we've been monitoring phosphorus going into that reservoir and coming out of that reservoir over time. And what we're seeing is that due to any number of management practices that we've implemented in the Susquehanna River watershed, that we are reducing the amount of phosphorus coming to that reservoir right before we get to the Chesapeake Bay. But if you look at what's coming out of that reservoir into the Chesapeake Bay, phosphorus levels are increasing. And that is a huge legacy effect, speaking to accumulation of legacies in that reservoir. And so again, it's a question as how do we manage those legacies within the river network there? Big issue in the Chesapeake Bay.
And does that kind of come back to your point that you made earlier around, the impact of nutrient use efficiency or the inputs into the system is, not a big meaningful impact to the output that you're discussing?
Yeah, depending on any number of factors, but yeah, that can actually be nominal compared to other things going on in the watershed.
Sorry, folks, we just have time for one more quick question and a quick answer. So, Adam.
Yeah, so gonna pick on agriculture again, but we talked a lot about assumptions and models and trying to understand if we can do solutions, how that might impact water quality. Trevor, could you maybe talk about, just to build awareness around this, is how are you guys working with agricultural retailers to figure out, better data of what's actually occurring in agricultural landscapes?
Well, just the Illinois Fertilizer Chemical Association is a member of our policy working group and very much engaged in this issue, having 4-hour field days annually and has speakers during their annual conference talk about water quality. So they very much make sure their members are aware of this issue and working on it. Do you have anything else?
I do. I think I know maybe what you're talking about. So I first of all, that fertilizer assessment that we have in Illinois actually has been any good idea gets copied across state lines. And so we are seeing that happen. It may play out a little bit different depending on state politics, but that assessment concept or checkoff concept is in existence in other states now. So that's great. Another good idea that keeps crossing state lines is the fact that, and we actually talked about this earlier this morning, maybe 10 years ago, farmers were not so comfortable with farm level data being collected about their practices, other than maybe NAS surveys, but specifically on their farm, what practices are you doing and the outcome of that. But what has happened is the groups in Illinois included, but other states as well, are working with ag retail because that's who helps them take on most of these practices to gather that information. And it's just now starting in a lot of states, but a lot of the efforts are either being paid in combination with these checkoff funds or actually some of the EPA funding that has gone to the Gulf hypoxia issue. So it's very exciting, but I think just philosophically, farmers are understanding that they have to be and the ag retailers have to work together to provide that data, or it doesn't exist and other assumptions are made in its place. So that seems maybe like not a big deal, but when we have communicated that that's in the works to a lot of different folks, including academia, people are very excited that that data will continue to be pulled. And across state lines, they're talking to each other, so there are going to be commonalities with what those data sets are showing. I'm assuming that might be what you had in mind. Okay.
But we need to cut this off, folks. Sorry, we have lunch. We have plenty of time for discussion during lunch. And Andrew, you want to say anything else?
Yeah, so with that, I wish we had 2 more hours, frankly, to discuss this. We do have lunch for 45 or so. So I want to thank the panelists for serving on the panel, and now it's time to break for some food. Thank you.